Here's a typical problem that we might see in a probability theory or some sort of regression type course. We want to verify that this function L, the negative log likelihood function, which is defined to be the log of the probability of the set Y given the set X and theta, is equal to negative the sum of the log of the probability of the YNs given Xn and theta. We want to justify every step, and that's super important here, right? We don't just want to jump to the answer. It's really, really important here that we know why this thing works the way it does. Okay, so let's start by making sure we understand what the notation means. We're looking at a data set D, which is a bunch of ordered pairs where the first one of the pairs comes from set Y, and the input value comes from the set X, and the result comes from the set Y. So X is a bunch of vectors, X1, X2, Xn, and Y is a bunch of targets. And there are capital N of these things according to this problem, right? So there's N rows in our data set. Right? And D is just a bunch of values, X values, and then what the Y value is associated with those X values. Now we want to assume here, and this is a pretty common assumption, that we have conditional independence. So observations are independent and identically distributed. Okay, so this means a couple of things. This means first that Yn, each of the outputs is conditionally independent given their inputs and the parameters. So the Yns are independent. And that we assume that each Yn depends only on the Xn's. So there's no cross dependence. Okay, so for example, if our X's were time, there's no lag dependence or anything like that. All right. So we've assumed that our observations are independent and identically distributed. We've talked about our data here. Okay. Let's start by talking about the probability of Y given X and theta. Well, this is going to be the probability of the Y's, the Y1, Y2, all the way to Yn, given X1, these are vectors, X2, Xn, and our parameters theta. Now, because these are independent, we can deal with each one of these y's separately and multiply the result. And because yn depends only on xn, then for any particular yi, the only dependence here is on xi, not x1 through xn. So this should be the product where we'll use n's. N goes from 1 to capital N of the probability of each yn given our input value xn and our parameters theta. Okay, so if this was, say, for example, 3, capital N equals 3, so 3 rows to this data set, we would have the probability of y given x and theta equal to the probability of y1 given x1 and theta times the probability of y2 given x2 and theta times the probability of x3, y3 given x3 and theta. Okay, so we've got this product here. And if we take logs on both sides, we look at the log of the probability of y given x and theta, we end up with the log of the product from 1 to n of the probability of the yns given our xn's and theta. But we know that the log of a product is the sum of the logs. So this is going to be the sum of each of the individual logs. So it's the sum of the log of the probability of yn given xn and theta. So if we define L of theta to be negative the log of the probability of y given x and theta, then it will indeed be equal to negative the sum from 1 to capital N of the log of the probability of yn given xn and theta. Okay, now that whole calculation again relies on this this IID assumption, and then from there everything sort of flows just using basic arithmetic.